Good afternoon and welcome to the 2022 Nobel Prize in Physics Colloquium. My name is David Haviland, and on behalf of the Nobel Prize Committee, I would like to warmly welcome you to this colloquium. Now, we started this tradition of sending a webinar during the COVID pandemic, and now that we're out of COVID and able to meet, we thought we would continue anyways, and we understand that several physics departments in Sweden are broadcasting this in the halls, and I'm glad you could be with us this afternoon to celebrate this year's prize in physics. The Nobel Committee is happy to do this colloquium and tell a little bit about our work in evaluating the prize and what we came forward to a conclusion. And the two experts this year who will present that are Professor Thors Hansson and Professor Larsson. Now, they'll give the colloquium, and afterwards we'll have a Q&A session where you can send in questions in the chat, or there's a Q&A window in the Zoom. If you're listening to us, you can type in your questions, and then we'll be able to read them up and field them afterwards. If there's nothing else to announce, then I would like to ask Thors Hansson to give the first part of the colloquium.
Thank you, David. Well, we start with what you all know, namely the prize winners and the citation. So there are three prize winners, Salle Spe, it's John Clauser, and it's Anton Zeilinger. And the citation is for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. And what I will do now is to give you the background and fill in what this motivation means. So we go, this is the outline. I will give you some background, talking about Bohr versus Einstein, a little bit about uncertainty relations, entanglement and EPR paradox, and leading up to Bell inequalities. And then it will be a discussion about the experiments that Mats will give you, and then I will come back and tell you a glimpse of the second quantum revolution, it's often called, and tell you about no cloning, quantum teleportation, entanglement swapping, and towards a quantum internet. So here we go. Bohr and Einstein, and I'm sure, since you are physicists, most of people listening, that there was a debate between Bohr and Einstein about quantum mechanics. Was quantum mechanics a complete theory? Was quantum mechanics internally consistent, or did it give rise to some kind of paradox? And Niels Bohr meant that quantum mechanics was indeed a good and complete theory. It had strange consequences, but that was something you just had to accept. Albert Einstein couldn't really accept that, and it was an ongoing discussion between these two giants of physics. And to explain what it was about, or one of the things it was about, we go back to the uncertainty relations. So here is Werner Heisenberg, and you know that in quantum mechanics, things that you observe is described by operators, like an operator for position, an operator for momentum or velocity, and so on. And these two operators do not commute, and you have this constant here, Planck's constant. Even if you don't know what is meant with that, I can tell you that this implies what is called an uncertainty relation. That is, if delta x means with what uncertainty you have when you determine the position. And now I'm not talking about an uncertainty that having to do with that you have crappy measuring devices. No, it's a fundamental uncertainty that you cannot avoid. And the same thing for velocity. Now, if you multiply those uncertainties, it has to be bigger than this constant, this Planck's constant. So you cannot simultaneously say, I'm at this position and I have this velocity, which you certainly can for classical particles. Now, I will explain to you an experiment or a thought experiment that Einstein, Boris Podolsky, and Nathan Rosen came up with, which they claimed that showed that quantum mechanics couldn't be a complete theory. And I'll explain it to you in a more modern version that was proposed by David Bohm. And the only extra thing you have to know here is something about the quantum mechanical quantity, which is called spin. So many elementary particles like electrons and protons, etc., but also photons, has the property that is called spin. And the simplest way to think of it is like really having a little ball that is spinning around. And it's spinning around an axis. So that axis has a certain direction in space. So you can ask, what is the coordinate for that vector? And let me call that Sx, Sy, and Sc is the coordinates of that spin vector. And it turns out that as a consequence, actually, of the relation I showed you earlier, you also have a commutation relation for these components. And from that, it follows that it's an uncertainty relation also for the components of this spin vector. So quantum mechanics tells you that you cannot simultaneously know exactly what is the Z component and at the same time, what is the Sx component of this vector. Okay, so that's the background. Now to the EPR experiment in this setting. We have a source, and that source sends out entangled pairs. We'll write down an equation later, but for the time being, let's just call them entangled pair or Bell pairs. So one of the particles goes over here to a detector, and here is made a spin measurements. And in quantum mechanics, these spins can only have discrete values. In the simplest case, if this was an electron, it could only have two values, up or down. And say that you measure here, and it's up, okay? Now, if you measure here, you will see that every time you measure up here, you measure down here. That's easy to see from the quantum mechanical wave functions. And that has to do with this entanglement. But you can, what you read here is completely random. Up, down, down, up, down. And the same here, it's random, but it's correlated. That by itself is quite strange because these particles all look the same. So why do you have such a correlation between measurements? But even more strange, and that was the thing that was considered as a paradox here by these gentlemen, was that say that you do this measurement, you measure up. So now you know what is the Z component of this spin vector. But now say that B here decides not to measure the C component, but the X component, the red vector. Okay. Then we get one value and knows that this particle has that value. But on the other hand, you could have said from the beginning that the C value was also known because of what was measured here. So that was the thing that they considered as a paradox, because this was violating this inequality, this uncertainty relation that I showed you. So The Einstein, Podolsky, and Rosen's, their conclusion was that they just cite the paper. They say, from this, the argument I gave you, follows that either the quantum mechanical description of reality given by the wave function is not complete, or when the operators corresponding to the two physical quantities do not commute, or equivalently, if there is an uncertainty relation between them, the two quantities cannot have simultaneous reality. And they have a technical definition in the paper what they mean with reality. But simply speaking, it is that it's something that is really there in the world, you know. And not surprisingly, they came out supporting the first alternative. So they say, we are thus forced to conclude that the quantum mechanical description of physical reality given by wave function is not complete. They felt forced, but let's note that they did not give a proof. There were these two alternatives. Schrödinger came to a different conclusion, the same as Bohr held. In this article, also from 1935, this was the same year as this EPR paper. They said, and you can read in German, I won't read it in my bad German, but I will say that the gist of what they are saying is that if you have a theory that at any instance, every instance tells you exactly what it is that you should measure locally for these particles, then that will always contradict some part of the quantum mechanical predictions. Okay, so that they come down on the other alternatives. But again, they did not provide the proof either. So you had these two ideas, these two positions standing against each other. So I said neither party could prove the thesis. And this was considered then more of a philosophical question, not really something for serious physicists, except perhaps, coffee breaks or something like that. And it remained like that for a long time, for years, for decades, until in 1964, John Bell gave this controversy, these two opposite ways of looking at the world, a mathematical formulation, and sharpened the question and opened up for experimental tests. So what did Bell do? Here is the famous paper that he wrote on the Einstein-Podolsky-Rosen paradox. And what he did was to construct a version of the EPR experiment, which was a little bit more complicated. And then he could mathematically show that the predictions of quantum mechanics could not be reproduced by any theory based on local hidden variables. That particular result that Bell had, although in principle you could check it in the lab by an experiment, in practice you couldn't do it because with real lab equipments, you couldn't perform that experiment. So here comes in the young John Clauser, one of this year's laureates that is on the picture here. And he thought that this result of Bell was very, very strange. And you have to realize how strange it really was, because what Bell said was that if quantum mechanics is correct, you cannot even think of these particles, these entangled particles, to carry some information with them. And when you measure, you sort of reveal what that information is. You cannot think of it like that. You have to accept that the quantum information is in this total entangled state. So Clauser said, strange. let's perform that experiment. Could quantum mechanics be wrong? Well, no. And this version, so-called the CHSH version of Bell inequality, that goes as follows. So now the change is here that these measurements, you can put the polarizer that tells you whether you measure spin in this direction or this direction. This was done with photons. So you don't really talk about spin, you talk about polarizations, although the basic sense, it's the same thing. Now, this vector that tells you what's the direction of this polarizer could be set in different directions. And so could this B here, that is the detector here that is run by Bob. This is run by Alice. A and B in this context is usually called Alice and Bob. That's the lingo of quantum information. Okay, so now you do the measurement. You send out these Bell pairs and you measure whether you get spin up or down, or whether polarization is in one direction or opposite to it for various settings of these A and B. And then you define a quantity, which is called S. And it's built up from correlation functions. So what does this mean? E of AU1, B2 means what is the average value, that's these brackets, of getting the result S of A1 and S of B2, where A1 and B2 corresponds to the settings of this vector and here vector in the two directions. And you look at several of these correlations and you take a particular combination of them. And then Bell could prove that this thing is less than 2 for any theory based on local variables. And note that no quantum mechanics goes into this. It's a purely classical reasoning that will derive this thing. And now here is the derivation. It's simple. There are many derivations. This is a particular simple and beautiful one. I won't go through it to you. If you read the scientific background to the prize, you will find it. But I just wanted to show you that it's so short and so simple. If you haven't seen it, I recommend that you look at it. And with that, I leave the floor to Mats Larsson, who will explain about the experiments to test this.
Yes, and what I will show you first is a purely classical experiment. So here you have the source, you have a detector here, and you have a detector here. The source here is sending out nails, classical nails, that are parallel to each other when they go into different directions. And then you, and then you have a very simple polarizer, just a thin opening in a metal plate here, and then you have a very simple detector. You just hear when the nail hits, and you get a hit, or you get or the nail is blocked. And you can set up a sequence of zeros and ones. 0 means that the nail has not been able to penetrate, to go through this thin opening. 1, of course, is that the detector has hit it. And this is a purely classical experiment. I don't think anyone has ever done it, but it would fulfill Bell's inequality, so that it would be less than 2 here in this case. What I'm going to talk about now is the experiments that shows a violation of Bell's inequality and the consistency with quantum mechanics. And I've taken these examples from a book called The Cosmic Code, written by Heinrich Pagels, and from 1982. I don't know if it's still in print, but I could really recommend it to younger students who would read more about Bell's inequality and so on. The very first experiment with entangled gamma photons in this case was done in 1950 by Madame Vaux and her collaborator Erwin Schacknow. And so what they did was to look for annihilation between an electron and a positron, sending out gamma photons in both directions. And what they were interested to measure here was the angular correlation between these two photons. This was not a Bell test. It was just a demonstration that you had an angular correlation between the two gamma photons sent in the two different directions. Later on, in 1967 at Berkeley, Carl Kocher repeated or did a similar experiment with, which was the first experiment with entangled optical photons. And this was part of his PhD thesis, and his thesis advisor was Eugene Cummins. So what he set up here was a cascade of photons. He excited the calcium atom up to a high level here. It decayed down to this level, and then there was a cascade of two photons, one at, in the more red region, and or 50, maybe green, and then one in the more blue region coming down here to the ground state. And because of the cascade, one could infer that these two photons were entangled. And this is the setup of his experiment. He had a calcium beam oven, forming a beam here, was crossed by this the light beam. This is a discharge hydrogen lamp. And then polarizer, lens and polarizer in each directions. And then, of course, the filter just to filter to select the appropriate photons, and then photomultipliers. And then he measured this in coincidence. And this was then published in Fish Rev Letters. And you can see here that the title is Polarization Correlation of these photons. So this was, shall we say, a very similar experiment to what Madame Wu and Jacquenot did. What you see here here is that when the polarizers were parallel, then he could measure time correlation between the photons in both directions. But when the polarizers were put into a 90 degrees angle, which means that one photon passed and the other one was totally blocked, there was no correlation between the photons. Once again, this was not a Bell test. It was only a test with the polarizers at 0 degree or 90 degrees. This was the paper that Hans mentioned, where they formulated this, what's now called the Bell CH-SH inequality. So what happened then? Clauser, who had been on the East Coast when he wrote this paper together with his collaborators on the East Coast, the CH-SH paper, he had graduated from Columbia University with Tadevs in molecular astrophysics, and was recruited to Berkeley by Charles Towns, who had Tadevs as a student. And Towns was just at this point pioneering radio astronomy, looking for molecules in interstellar space. And he wanted to have a postdoc for this project, so he recruited Clauser. Clauser, as you had seen, had already become interested in the foundations of quantum mechanics. And he was well aware when he came to Berkeley that Kocher's experiment was still around, although Kocher had left Berkeley. So he started to discuss this possibility of this experiment with Towns and Cummins. Cummins was negative. He didn't feel that what's the point in testing this inequality. Towns, on the other hand, the laureate in physics in 1964, the person who really invented the laser principle and got the Nobel Prize for this, he got interested. And he, of course, with his authority, he persuaded Cummins that they should collaborate on this. Cummins agreed. So they made an agreement where Clauser was allowed to work 50% of his time on rebuilding Kocher's experiment, and Cummins provided a PhD student, Stuart Friedman. So it was really the team, Friedman, Clauser, who worked on this rebuilding the Kocher experiment. They had already directly identified the polarizers as the weak point in the experiment. it would have taken infinite amount of time to do the experiment with the Kocher's polarizers, but there were also other improvements that were needed in order to get this experiment to work for a Bell test. So after 2 years of work, they had come up with this experiment. They still used the calcium beam. They used, which you see here, they used in this case, instead of hydrogen, they used for some reason deuterium, and maybe it worked better. And then they rebuilt the polarizers completely and increased the distance between the detectors by a lot, by probably more than a factor of 10. And here you see the coincidence, the electronics and so on. Instead of, so they used something called pilot plates polarizers that are much more effective than those that Kocher had access to. And yeah, here you can see the experiment in reality. I mean, you have here the stack of polarizers, and then you see you have to rotate the polarizers. So they were rotating the polarizer 22.5 degrees, took data, and then made rotation, took data, rotation, took data, and so on. And this went on and on and on automatically. They didn't have to do it by hand. So they went on for hundreds of hours, taking the data. And here you can see first what you have up here is the version of the inequality that they derived. And if this inequality for a local hidden variable theory should be, this quantity should be less than 0. These are the coincidence rates with polarizers and without polarizers. This quantity should be less than 0. And they measured, but now can you see it? Is it possible to remove that?
They can see it, it's not there.
You can see it?
Yeah.
Okay, because what you can see is that this delta is equal to 0.5. Which is of course much larger than 0. So what they could demonstrate was that the inequality is broken by 6 standard deviations. And here you also see the result as a function. What you have on this axis is this ratio between the R with polarizer and R0. And you can see here that these are the data points that they took during 200 hours. And this full drawn line is not a fit to the data. This is the quantum mechanically derived curve. So it's really a very good agreement with the quantum mechanics. And this was published then in 1972, and this was the first real Bell test. And this is a picture I've taken from a book named The New Quantum Age, published in 2012 by Andrew Whittaker. And this is just to emphasize that local hidden variable theories, then this value S that Hans discussed should be between -2 and 2, but quantum mechanics for a number of different angles between the polarizers will break. We'll have a larger value here and a larger or smaller value here, a larger negative value here than local hidden variable theory. But in the experiment of Friedman and Clauser, and I should say at this point that Stuart Friedman passed away in 2012, the polarizers were at fixed angles during the data taking, so rotating fixed angle, taking data and going on like that. But the question that Bell posed was, is it possible to rotate the polarizers so quickly so that after the photons already left the source, the photons don't know what setting the polarizer will have? Well, it's technically not possible on an experiment of this scale to rotate the polarizer so quickly, because we're talking now about, say, 10 nanoseconds or so. So Aspe, he had got interested in this also and had met Bell and discussed this with him. He came up with a proposal for an experiment where you have 2 different channels where there is a switch here and a switch here. So after the photons have left the source, they still don't know if they're going to go in this direction or they're going to go in this direction to another polarizer. and the same goes for the other side. So that, and these switches, they are so quick so that they can switch in 10 nanoseconds about, which means that you had an experiment where the photons, once they left, they still didn't know in what branch of polarizer they would enter. And it took some years for Aspect and then collaborators to design this experiment. They actually did it in 2 stages. They did first a repetition of Clauser-Friedman experiment using, in the first instance, a laser, 2 lasers to excite instead of a deuterium arc lamp, which means that they got much better statistics. In another experiment, they also used 2-channel polarizers to even further increase the statistics. So they had not 6 standard deviations, but more than probably like 40 standard deviations in their experiment. But it was this experiment that was the most important with these time-varying analyzers. And here you see the real experimental setup that they came up with, and which was actually a quite difficult experiment to get all the optics correctly working. And of course, they could not reach the same high level of number of standard deviations, but the relation they could test in this particular setup, S, if in a local hidden variable theory, should be between -1 and 0, but they measured S as 0.101, which breaks the, which is 5 standard deviations. So this was an experiment that caused a lot of attention, not only in the scientific community, but also in the press. Here you see from Swedish newspaper, Svenska Dagbladet, September 1st, 1982. And of course, here you have all the drama that's needed in order to catch the attention. I mean, you have Einstein. Einstein may be wrong. Signals can travel faster than light, which is not possible. This was not the outcome of this experiment, but this was the interpretation. So it really caught a lot of attention. Now we're coming to what was the importance of the Bell tests. And here I'm going to hand over to Hans again.
Yes.
Hans, let me interrupt. The cursor is not working, so you have to just narrate the slide, no pointing. Sorry.
Okay.
But I could see it better. They can't see it in Zoom. Oh, sorry.
So, well, what was the importance? It was, of course, a foundational philosophical implication, and that we already discussed in the connection with Bell's original work, and also Mats has discussed the experiments. Another important thing was that it provided techniques for producing entangled pairs and to manipulate them, to measure them. Now, modern experiments are using other techniques, but this was the first time where you showed that you could actually do this with optical photons, which was very important for the continuation. But perhaps even more important was that people realized that entanglement in Bell pairs is a quantum resource that you can use in order to achieve new things. And I'll give some examples. And another thing to the end, if I have time, also say that the actual Bell tests, not only entanglement by the Bell test is important if you want to have some super safe, or as it's called, device-independent quantum cryptography. So one thing that you want to have is to have established entanglement over long distances, because the goal is to have some kind of quantum network, or perhaps even some kind of quantum internet, where quantum devices in nodes can talk to each other and share entanglement so they can do quantum operations together. And that's difficult because the entanglement is brittle. That if you send photons through optical fibers, there are losses, there is noise, and you lose it. And you cannot use an ordinary amplifier because that also destroys entanglement, something that has to do with something that is called the no cloning principle, which says that if I give you an unknown quantum state, you cannot duplicate it and give me back two quantum states which are identical. That's not possible, but that's actually what an amplifier is doing. You can't amplify with normal amplifiers. And I will give you now an example, also something that is called entanglement swapping and quantum repeaters. Now, the principle of no cloning is also extremely easy to show why it doesn't work, has to do with the linearity of quantum mechanics, but because of time, I will not give you the formulas. So let's go directly onto entanglement swapping. And this was an idea that came up by, conceived by Anton Zeilinger, and he also did the experiment. So for that, you have to know that there are, unfortunately, I cannot point now because the technology doesn't work, but you have 4 Bell states. I've written them here. They are called psi plus minus and phi plus minus. Now consider an experimental setup where you have 2 sources of Bell pairs, not 1 as we had before. So you have 4 particles. Particle 1 going out here to the left, particle 4 going out to the right. They've never been close to each other. They move out. The 2 others move together. What is this?
He's doing that.
2 others, 2 and 3, they come together. Now you make a measurement on those, and then you can entangle them. So the way it works is the following, that you start with a state, which is just a product state of 2 entangled state, 2 Bell state. I call them here 5 plus 1, 2, and 5 plus 3, 4. Now it's just a matter of algebra to rewrite that as a linear combination of states which has an entanglement between 2 and 3 and 1 and 4. And then with the usual principle of quantum mechanics, if you project on one of the Bell pairs of 2 and 3, in that case, which is the lowest equation here, this state 1, 2, 3, 4 turns into the product state of an entangled state between 1 and 4 and one of 2 and 3. So by entangling 2 and 3, then like magic, you have entangled 1 and 4. And then you can do this in sequence, and you can in principle build up a network. So that's entanglement swapping. And this was the first experimental paper.
Yes, and sorry. So let me, since I cannot point, I'll try to walk you through this experiment. If you look at the left, you have a UV pulse created by a laser. The UV pulse is sent into a plate that is called an EPR source. This is a nonlinear crystal that will cause something called parametric down conversion. You send in a photon, high frequency photon, and you get out 2 entangled photons with lower frequency. Then this UV pulse is reflected on a mirror and goes back through this nonlinear crystal one more time. In the first passage, you create photons 2 and 3. You create photons 1 and 4. And in the second passage, you create photons 2 and 3. And you send photons 2 and 3 up to a beam splitter where they have 50% chance to go to different directions, or they can also go in the same direction. If they go in different directions to 2 different detectors, you can do coincidence measurements. And this is when you have demonstrated that they were entangled. And then, as Hans explained, this means that the 2 photons 1 and 4 automatically becomes entangled. And how do you demonstrate that 1 and 4 are entangled? Well, you have once again a setup of polarizers. and detectors and coincidence measurements. And then you look for the correlation. And if this correlation fulfills theory, then you get this. Here you can see the angle between the polarizers and the coincidence rate. And there is an almost perfect agreement between what is predicted by quantum mechanics and what is measured by the experiment. So this means that in this case, photon 1 and 4 are entangled, although they never had anything to do with each other in the past. So I leave it now to Hans to explain why this is interesting.
Yes. So by having entanglement swapping, if you also have a quantum memory, in that case, you can build a quantum repeater. And if you have a quantum repeater, then you can start to build quantum networks. So the quantum repeater, why do you need a measurement? Well, you can see here, this S's here tells you that it's the swapping events that I explained to you about. But of course, if you go from A down to B here, it takes some time. So A has to remember what quantum state it was before you establish B. So you need memories. And that is, at present, that's the thing that is sort of the bottleneck here. And people are working in developing good such quantum memories in order to build such network. But this is something that is going on now. It's current research. You can also get long-range entanglement in different ways. Instead of sending the signals through optical fibers, you can send them through air or even through space. In 2015, there was an entanglement via an optical link from the island of La Palma to Tenerife. Here is the telescope, then one of the telescopes that used it was Zeilinger's groups who did this. So they entangled over 144 kilometers. You cannot do that with one optical fiber. And even more amazing, they used later, a couple of years later in 2018, the quantum satellite MICUS that was launched by the group of Jianwei Fan, the Chinese Academy of Sciences. So that's a quantum satellite, and with the help of that, you can establish entanglement between China and Austria, 7,600 kilometers. Again, this is frontline of this kind of research that is going on now. More on entanglement. And I think time is almost run out. So I will just mention perhaps one or two of these points. So far, we discussed only entanglement of two particles, but it's also interesting to look at entanglement of many particles. And the simplest thing is that you have three particles, then you can form this state. I've written down here the psi DHS for Kutzwiller, Horn-Zeilinger, Greenberger, Horn-Zeilinger, thank you. And this state is interesting because by measuring, doing just a finite number of measurements on these states, you can establish violation of a Bell inequality without doing any statistical analysis. So that's an interesting thing. And if you want a very simple, beautiful explanation of that, I would recommend this paper by Mermin. It's very pedagogical and worth reading. Entanglement is now also used in theoretical physics, in the study of topological phases in condensed matter physics. The entanglement patterns differ between different states depending on the topological properties, and that has been used in order to classify topological states of matter. One of the most influential person behind that is Yang-Dong Ben. Quantum cryptography or quantum key distribution is yet another very interesting topic. And not the least because it's also been put into practice. There are quantum cryptographical protocols. The first one, it's called BB84, after Bernard Besar, and done in 1984. That doesn't use bell pairs. It uses other properties of quantum mechanics. In 1991, Arthur Ackett had another protocol for quantum key distribution that is based on entanglement, and that was actually used in this Tenerife to La Palma experiment I talked to you about. And in 2022, 3 groups used loophole-free tests to realize what's called a device-independent quantum key distribution. That means that if the evil eavesdropper, it's always called Eve in quantum information connection, has access to your devices, still you can make sure that that the quantum code that you send is secure. And I should just end here with a comment on these loophole-free bell tests, because we talked about these locality loopholes, but there are others. And some people say that, why do you care about that? It's things like, you know, other detectors trying to fool you or something like that. That sounds a bit paranoid. But of course, you shouldn't be paranoid about nature, but you should be paranoid about Eve, because Eve tries to deceive you. So this work to get loophole-free bell tests, it's also Zeilinger was one of the groups who achieved that, has been important in this development of cryptographic devices. So yes, I leave you with this for a moment, and then we are ready to take questions.
Okay, thank you, Hans and Mats, for that colloquium. And it's open now for questions. And I'm looking at the Q&A here on Zoom and not seeing anything coming in. We have 160 participants. That's nice. And I know many of you are in lecture halls where there's some local experts who are going to be answering. But if you'd like to type in a question in the Q&A, we have a couple minutes and you can do that now. So as they say, this colloquium was sponsored by the Nobel Committee for Physics, and we hope to make this a yearly tradition where the physics departments in Sweden can be informed right after the Nobel Prize about the year's Nobel Prize. So we hope you'll join us next year, and we'll be able to do the same thing. I'm not seeing any questions in my Q&A. I hope it's working. I apologize. We had a little bit of problem with the pointer not working. The cursor was not working with the system here at KVA, at the Academy where we're broadcasting from. Nothing coming in on Q&A? Okay.
And that's because at most places there are local experts,
yeah, exactly.
So they can interact directly with the...
Right. Okay, then, here's a question that's come in, right? So what were the technical advances of the Clauser experiment? I think that's a good one for you, Mats.
Okay. Yes, I would say that the main technical advance was that big improvement of the polarizers. And that was something that Clauser realized already when he came to Berkeley, that with the polarizers that Kocher had used, the experiment would not be possible to conduct. So that's why they spent so much time on rebuilding and building up these pilot plates. Polarizers, and as you can see, they increased the distance between the detectors by more than a factor of 10. I think Kocher had maybe 40 centimeters between the detectors, whereas Clauser and Friedman increased this to 5 meters. And there were a number of other improvements also. I mean, but I think the polarizers was the one that one should really point out, and this took a long time for them.
Here we have another question coming in. Hans, you said how to quantify entanglement question, Mark, and that's difficult. What is your favorite current way to quantify entanglement? if you have them?
That is not my field of expertise. It's a big field. One thing that I know of, which is easy to understand, is the thing that is called distillation. That is, if I give you a big multi-particle state which is entangled, and then I ask you, could you give me back the number of bell pairs? Then the number of bell pairs that you can distill by using local operations in this system. That is one measurement of entanglement, but there are also other measurements of entanglement.
Thanks. I can also answer that one. My favorite test is the Schuken-van Luke test. We just recently used it to try to verify entanglement in microwave frequency combs. Okay, so anonymous, you said, did Bell comment/write on these experiments? Which of you would like to answer that? Did Bell comment or write on these experiments?
As far as I know, yes, Bell was very interested in these experiments. And I know that when Aspe started to think about how one could try to sort of pass the low pole of the locality, he definitely went to see Bell. And so, yes, definitely Bell had contacts with them. But you should also be aware that unfortunately Bell passed away in 1990. So he could not follow this, the later development he was not able to follow.
And perhaps I can fill in one thing there, and that is that Bell was actually interested in some of these alternatives to quantum mechanics or modifications of quantum mechanics that has been proposed. There are a number of such modification that sort of changes the Schrödinger equation, and which you can test experimentally. So far, all experimental tests, as in the range where they've been done, has excluded them. But it can be good to remember that John Bell just didn't laugh at it as many people do, but he took it seriously.
Okay, there's another question here. How did Aspe perform sufficiently rapid switching of the optical path? I think that's your, okay.
Yes, he had acousto-optical modulators at each end, or as a switch on one side and the other side. And this was creating a standing wave in water, so that I don't have a view graph of that particular picture from his publication, but basically every 10 nanoseconds, the photons were switched in either one of the arms or the other arm. And then, of course, you had these transducers that created these standing waves in water, but one transducer at one end and at one switch and another one at the other switch, so they were not coordinated. And in this way, he could have a almost random change of how the photons went when they came to the switch in both directions and went into the different paths and met different polarizers.
Are there any remaining advocates for hidden variables? Does anybody know the answer to that?
The one thing that is stressed here was that it was a statement on local hidden variables. And you might know that it's something that is called Bohmian quantum mechanics. And that is a hidden variable theory, but it is non-local. And one way to understand it is that basically phase of the wave function is something that tells the particle, you know, a path to follow. So there you have real paths, but it's non-local. As far as I know, there isn't any, you know, testable non-local hidden variable theory at present.
Well, I can add that I know that the Nobel laureate from, let's see, what year was that? Gerhard Toft. He is working on some sort of super deterministic theory. And he is fully aware of all the problems with such a theory. But, and of course, if he eventually could come up with something that could be tested against quantum mechanics, that would be very interesting. But I think we are very far from that. And he knows it, I'm quite sure.
Okay, how can I think of these entanglement of this entanglement quantification schemes in terms of continuous variable systems? How can I think of entanglement quantification schemes in terms of continuous variable systems? You have a good answer to that. Yeah, that's I don't have a simple answer to that. I think I know what the question's getting at.
Yeah, I think that I have seen statements that it's difficult to formulate Bell inequalities for continuous variables. I haven't seen, I've heard people claiming that. I have not seen any proof of it. But I know it's something which is it's a non-trivial question.
Non-local in space or time? Non-local in space, time. Both and, I would say, not or.
Or, no, right, local in space.
Yeah, what you want to avoid is the possibility to signal, from one measurement to the other. And there you have to assume in the experiments that was done by Asper, he assumes that special relativity is correct, namely that there is an upper limit to signal speed. If you don't believe in special relativity, then clearly you cannot make the experiments, because you could always assume that, the signal would move faster. So that's underlying these claims of locality.
And I think this should be our last question. It's a long one. Mats, in your opinion, when was the experimental status of Bell tests settled by usual physicist standards? And there's a caveat here. There are experiments closing loopholes as recent as a few years ago, but they seem increasingly to focus on paranoid issues in cryptography and less on testing quantum mechanics, presumably because it's viewed as completely settled?
Yeah, that's a difficult question. I mean, using normal, shall we say, physics standard, the question was settled already by Clauser, because he did an experiment, and Friedman, of course. I mean, they did an experiment. They could establish a violation of Bell's inequality by 6 standard deviations, and that would normally be considered as a totally satisfactory test and wouldn't really require any more experiments. But on the other hand, we know that Bell was very concerned about this problem of locality. So I think that definitely the first Asper experiment overcoming this locality was an important step, and also considered by Bell himself to be an important step. Then I think one can have the view that the development then took place. You can have the opinion that this was conspiracy theories, but it was also something that drove the technology forward all the time. And in particular, the change of using these atomic cascades that both Clauser and Asper used was replaced by parametric down conversion. And this really opened up the field enormously, because you got a source that was so much more effective than the atomic cascade source, and this spontaneous parametric down conversion. And I think I read somewhere that Zeilinger, when he started using this new source of entangled photons, if I remember correctly now from reading one of the papers, he could establish 100 standard deviations in 5 minutes. So that's...
So I can complement perhaps one thing about these loopholes. And there are many loopholes, something, for instance, called the free will loophole. But the other loophole, except for the locality thing that people have worried about, is what's called the detection loophole. Because you can show that if you have inefficient detectors, and of course, no detector is 100% efficient, but if you have detectors which are too bad, then you can violate, then you cannot exclude hidden variable theories. So there is a limit, I don't remember the percentage limit, that you must have on your detectors and the efficiency in order to do that. And then it was a race to have both something that could ensure locality and something that at the same time could have sufficiently good detectors to close these two loopholes. And these references that I gave you was the experiments that simultaneously closed the locality and the detection loophole.
Okay, I think we'll wrap up the questioning with that. And I want to thank you all again for joining us on this colloquium. We hope to see you back next year for the 2023 Nobel Prize. So from the Royal Swedish Academy of Physics and on behalf of the Nobel Committee, thank you for attending.